This conference will now be recorded.
All right, Dominic's saying it's clear. So, yeah. Well, let's go back to finishing question number 18. Question 18 was one that you guys asked about and said that, and I said that it's kind of an often asked question. You'll see it again in the energy unit. We haven't studied energy yet, but it turns out that kinetic energy is proportional to the square of an object's speed, and that comes out here too. They're saying a car of mass m slides across a patch of ice at speed v with its brakes locked. It then hits dry pavement and skids to a stop at distance d, and the coefficient of friction between the tires on the road is mu. 18 says, well, what would happen if we doubled its mass? And 19 says, what will happen if we double the speed? For starters, this is a dynamics unit. We're going to end up using F equals ma. And if I were to make a free body diagram of this car that is sliding with friction, we'd have a frictional force going to the left, a weight force going down, a normal force going up. By the way, this is assuming that the car is going to the right. So the car's initial velocity is going to the right, and then it brakes, and so the acceleration is to the left. That's why the frictional force is to the left. So we can say that friction is equal to ma. That's really what we're saying. So I'm replacing F net with the frictional force. And friction is dependent on mu and the normal force. Those are things that are not changing. And so they're asking about how far it's gonna go. So this sounds to me, since they're asking questions about distance, this sounds to me like a kinematics problem. And I'm going to use the third equation. I'm going to say that VF squared is equal to VO squared plus 2A delta X. And the final velocity is going to be 0 after it comes to rest. And so I'm going to solve this for delta X. It's going to be negative VO squared. Technically, it's going to be 0 minus VO squared divided by 2A is equal to delta X. So if the initial velocity stays the same and the acceleration is only going to be affected by mass, right? So take a look. Let's go back over here. If I divide both sides by mass, I get mu Fn over mass is equal to A. So if I don't change anything in the numerator and I increase the denominator by a factor of 2, then the acceleration is going to get smaller by a factor of 2, meaning if I don't change the frictional effects, the larger mass is going to cause a smaller acceleration. And if the acceleration goes down by a factor of 2, we can see from this relationship here that the stopping distance, delta x, is going to go up by a factor of 2, which is, now wait a second, I've screwed this up. And here's where I made a pretty critical mistake. I made a mistake by saying that mass is only down here in the denominator. And so let me rewrite this in the blue box right here. The normal force is dependent on the weight, mg, since it's on a flat surface. So when I double the mass, it increases in both the numerator and the denominator, and the acceleration doesn't change. That was a sloppy mistake that I just made, so I apologize. So since the mass of the vehicle shows up in both the numerator and denominator, it cancels out, the acceleration stays the same, and therefore if the acceleration stays the same, it's not decreased here, the stopping distance remains. Conversely, if I go ahead and just take a look at 19, even though you didn't ask about it, if the acceleration stays the same, we don't do anything to the mass, but now we're only going to look over here at this expression. If I double the initial speed, VO, it gets squared. So I basically get a 4 in the numerator, which means that the stopping distance required for the same acceleration goes up by a factor of 4. That's where choice E comes from in question number 19. You guys might see that in like your driver's ed classes. They might bring this up. They won't do dynamics and kinematics in the driver's ed class, but they certainly will discuss, hey, you need 4 times the stopping distance at twice the speed, and that's because of this relationship. It's VO squared. Hopefully that answered your question, even though I made that mistake on mass there, Jess, on question number 18. I'm going to backtrack a little bit, and I'm going to go back to Eleanor's question on number 18 on the second review packet. Let's make sure that I answer that question, and then I'll go down from there. Here's question 18 on review packet number 2. It's an Atwoods machine problem. And, you know, I've said this a bunch of times in class. It's definitely something you should plan on seeing. My strategy that I've recommended is saying, okay, well, since the system, we're told that the system is going to accelerate towards that direction because M is accelerated down. So let's call anything that goes up on the right side, let's just say anything that causes the system to rotate in that direction is positive. So really, one way of thinking about it, and you don't need to sketch this, you know, on a test, but maybe conceptually in your head, you're thinking, all right, well, the weight of just mg of this mass right here is to the right. That's going to be negative. And the weight of this one, which is going to be mg, is going to be positive. So really, the dynamics equation, if those are the only two forces involved, it's going to be mg, which is positive, minus m1g, which I'm just going to plug the number in, 1 times 10, is equal to the total mass times the acceleration of the system. So this becomes m times 10 minus 10 is equal to the total mass, which is 1 plus m times a. And a we were given in this problem, it should be 5. Yep, it is 5. All right, so let's go ahead and make that substitution. And then I'm going to distribute that 5 to both terms in the binomial 1 plus m. So that gets a 5 and that gets a 5. This becomes 10m minus 10 is equal to 5 plus 5m. And then I'm going to group my like terms. I'm going to subtract 5m from both sides. So I get positive 5m on the left. I'm going to add 10 to both sides. So I get 15 over here, and I get m is equal to 3. So that's my approach and solution to solving that Atwoods machine question number 18. Eleanor, make sure that that makes sense. My gut feeling is that maybe you didn't include the total mass in the system, but either way, let me know if you have a follow-up. So let's see what is next. Ryan is asking a question about airplanes dealing with lift. Not directly, to be honest with you, that would be unfair to ask about a lift force. By the way, this is not what you were thinking, but if this is the cross section of an airplane wing, right? So that's looking at the end of the wing tip. And so the wing tip kind of extends into the fuselage of the plane. This is my best sketch here on the fly. So here's a propeller at the front. And so this is what I'm trying to draw, is the shaded edge of the wingtip. And this is a question about Bernoulli. And so what happens is that the airstream across the top has a larger distance to go. Initially, they're at the same pressure. And then all of a sudden, the air that goes around the top of the wing has to go a farther distance, so it speeds up, which actually drops the pressure down. And the air across the bottom is at a higher pressure. And it's the difference in pressure underneath the wing and above the wing that generates lift. Now, that would not be a fair question to ask. It would be fair to say that a plane is flying and has a certain amount of lift force that's equal to its weight, but we couldn't get into the fluid mechanics of that portion of the question. Make sure I've answered your question. Let's move on to Marika is asking about circumstances in which we would switch to positive and negative directions. Yeah, so in this question, Marika is saying, more generally, not about a specific question. Traditionally, we say that left on a coordinate axis in the horizontal direction, left is negative and right is positive. And if things are moving up and down, up is positive and down is negative. It's certainly convenient to do it this way because this is what we're comfortable with on a coordinate axis. We draw these a lot in our math classes. My advice is, from here on out, anytime something is accelerated, call the direction of acceleration positive. So, for example, let's say I take a ball and I drop it in a gravitational field and it falls downward. And let's say that there's a small drag force. I don't know, maybe the ball has a parachute or something weird like that. So, since it's accelerating down, and at least initially, then it might make sense to call the downward positive and upwards negative. That way, my dynamics equation becomes, in this case, mg minus the drag force from the parachute is equal to my net force, ma. Now, I'll explain why I think it makes sense to do that. In this case, the weight is larger than the drag force, which means that the acceleration is going to be downward. And if I make downward positive, it's less likely that when I have to plug in a number for acceleration, whatever it is, in question number 18, it was 5, but that's not related to the ball parachute question. Eventually, I'm going to have to plug a number in for A. And oftentimes, by that time, I find that students will forget to make it a negative number if it was downward, and they had a traditional coordinate system like this. So, the advice is call whatever the direction of acceleration positive, but only for convenience. On the flip side of that, if you are a traditionalist and that bothers you and you'd rather always stick with up positive and down negative, that's totally fine. There's no requirement, there's no mandate to call the direction of acceleration positive. It's just there to avoid those kind of sign errors that I see a lot. So, Marika, make sure that I've answered your question about vector directions. Nina is asking about 8, and Jess is asking, I think we did 18 already. So let's take a look at Nina's question, which is number 8 on review packet number 3. So Nina's asking a question on an Atwoods machine. Again, the thinking on this is when you see one, you should, the first thing that jumps into your head is, I'm going to destroy this because I'm so well prepared. I know there's an Atwoods machine question coming. We can see that the 3 kilograms is way bigger than the 5 kilograms. We don't need a physics class to know that the direction of acceleration in the system will cause the pulley to rotate in the clockwise direction. The 3 kilogram mass is going to accelerate down, and the smaller 1.5 kilogram mass is going to accelerate up. So now I'm going to basically just conceptualize this in my head and call everything going this way positive, everything going this way negative. And I'm going to put some numbers in here for the weight. I'm going to use G as 10. That means that there's 30 newtons of weight pulling that way and a smaller 15 newtons of weight pulling to the left. And so for question number 8, the net force in the system is 30 newtons. 30 minus 15 newtons. So the net force, if I just write out Newton's second law, the net force is the total mass times the acceleration. This is going to be 15. The mass in the system is going to be 4.5. And so now I have enough information to solve for the acceleration of the system. it's going to be a 15 over 4.5, which gives us something just over 3, right? If this was 5, then it'd be 3. So that's where answer C comes from in question number 8. Nina, make sure that I've answered your question. Dominic is asking about 1 and 4. And then I got a question also about number 2 on packet number 3. So let's do that. Let's take a quick look at question number 2 in packet number 3. I haven't fully read the question yet, but as soon as I scanned it, I saw the words initial velocity, and I saw that it went 8 meters. I saw that it had there's a rough horizontal floor. So rough horizontal floor means you can't ignore friction. And this information here, the initial velocity and the horizontal displacement here, should smell like kinematics to you. You should be like, yep, I'm being given acceleration data just without acceleration. So I know that it comes to rest, so the final velocity is equal to 0. And if I knew A, that would make this problem much easier. Let's go ahead and imagine for a second that I didn't see that stuff at first. I should be thinking, okay, there's a free body diagram here, mg going down, normal force going up, it's sliding to the right, but there's a frictional force to the left. And so friction is the net force, ma, and friction is equal to mu mg. And they're asking me in question number 2 about the coefficient of friction. The m's cancel out, and so mu is equal to a divided by g. Well, g is known. If I only knew the acceleration, I could solve this problem. And so I can solve for the acceleration by using the kinematics information that you're seeing me kind of get going up here. I'd use the third equation, vf squared equals vo squared plus 2a delta x, and I'd solve that for a. The final is 0. The initial is 4. I'm going to leave the units out here. It's getting a little messy, and I have to divide by 2 times delta x, which is 8. And that's going to give me my acceleration. In the numerator, I get negative 16. In the denominator, I get positive 16. So the acceleration is negative 1. So I get negative 1 over 10 in this case. And so we get g is equal to 0.1. And that's where choice D comes into play for question number 2. Make sure that that I've answered your question on number 2 and packet number 3. Jess, why is friction? Is your question? I'm guessing that your question on why is friction equal to the net force related to question number 2 here. Let's make a sketch of what's going on. Just make sure that you're talking about question number 2. If there was no sketch here, but here is the object, whatever this is, this kind of box, and it's sliding, it's going to the right. So I'm going to just put some, like, I don't know what you call those, wind marks or something like that. And so if I were to kind of superimpose a free body diagram on top of this, I have a weight force going down and a normal force going up. And there's only one force acting in the horizontal direction, and that is the force trying to get this thing to stop. Eventually it does stop because friction is acting horizontally. So the sum of the forces in the y direction is equal to 0, and my dynamics equation would be Fn minus mg is equal to 0, and Fn is equal to mg. In the in the x direction, the sum of the forces is not equal to 0. So the only force acting is friction, and so I'd say that friction is the net force. And that's where my next step goes to right there. Mu mg is equal to ma. Just make sure that I've answered your question. It's not uncommon for students to really get confused with this concept of inertia. The box is going to the right. It has a tendency to keep going to the right, but that doesn't mean that there's a force acting there. It just does that because it has this inertial property, which is a property of mass. The more mass it has, the larger this tendency is to keep going. By the way, and it's kind of interesting and not directly related, it's indirectly related to what we're doing, but the inertial behavior of mass was actually only recently formally discovered by the Large Hadron Collider in CERN. This is in Switzerland, the European Atomic like particle physics agency. And it was first proposed in the 1960s by a British national by the name of Peter Higgs. And he proposed that there's a particle in all objects that have mass. There's this Higgs particle that he called a boson. That word just simply means really, really small particle. And this Higgs boson interacts with a field that almost like, you know, moving your fingers through molasses. It's this kind of resistive field. And so the inertial effects of mass are simply a particle interacting with this Higgs field. Anyway, the reason that I thought that I'd mention that is here we are discussing inertia when you know, most people assume that the book on understanding mass was closed, you know, 500 years ago, and that's not true at all. The most recent chapter, the book was finally closed on fully understanding on the most granular level what mass is and why it behaves that way, only a few years ago. All right, let's stick to what we're doing here. I'm just gonna kind of see where I am. Dominic's asking 1 and 4 on packet number 2. I've got a question for 23 on packet number 1 and 13 on packet number 3. Let's do Adam's question real quick, and then I'll go to 1 and 4 on packet 2. Adam's question is on number 13. Tractor trailer question. The mass of the trailer is 4 times the mass of the tractor. The tractor accelerates forward. The force of the trailer applies on the tractor. There's a lot going on in this question. This smacks of a Newton's third law question. What is the force that the trailer applies on the tractor? Well, that's the same as the force that the tractor applies on the trailer. So, and that's all this question is. It's just simply asking the question. It's not asking what that force, like how big that force is in terms of F. And so at first there seems like a lot going on, but once you read through these questions, this is simply a Newton's third law question. And you'll remember that really simple kind of worksheet that we did, at least the front side of that conceptual development worksheet was easy. It was, you know, bat hits ball, ball hits bat, fist hits, you know, desk, desk hits fist. And so the force of the trailer applying on the tractor is equal to the force of the tractor on the trailer. Done. That's all this is really a Newton's third law application question. I'm glad you asked it, Adam, because you'll see these from time to time. And if you let it be as easy as it is, you'll be in good shape. You know, all of us, myself included, assume that all these questions are layered like an onion, and you have to peel them out. It's kind of like peel them away to really understand them. But this one was down the middle. Adam, make sure that I've answered your question. So let's do one more. Connor's asking about 20 on packet number 3. Then I'm going to switch it to a different one. Here's question number 20. 500-gram ball moving at 15 meters per second slows down uniformly until it stops. Again, you know, a lot of kinematics data here. The initial velocity, then it stops. That's the final velocity. And then we're given the horizontal displacement here. I haven't even read the question yet, but I'm pretty sure I'm going to need the acceleration from that information right there. If the ball travels 15 meters, what is the average net force? Well, I can say that the net force is equal to mass times acceleration, where the mass of the ball was given to me as half a kilogram. And if I knew the acceleration here, then I can answer what the net force was. So I'll go ahead and do that. I'm going to use the third equation, VF squared equals VO squared plus 2A delta X. Solving for A, I get V final squared minus V initial squared divided by 2 delta x is equal to a. It becomes 0 squared minus 15 squared over 2 times 15. So I'm going to use my calculator. 15 squared divided by 30, and I'm getting 6750. I'm not sure I did that right. All right, so 15 squared divided by 30. Yeah, I'm getting 7.5. I should have been able to do that this way too, right? This 15 cancels out with one of the two. 15, I get 15 over 2 is 7.5. Anyway, the acceleration is 7.5. So when I plug that in there, half of 7.5 is where answer B comes from. Connor, make sure that that I've answered your question. Sean is asking about the recorded video. I am recording now, but I started like maybe 5 or 10 minutes into it. I don't know why, I just forgot. So we just didn't capture that first 10 minutes. It usually takes about an hour for the compression to occur, and I'll post it afterwards. So probably around like 9, maybe after 9 o'clock tonight. I'm going to backtrack. There were some questions on packet number 2 I'm going to take a look at. Specifically, Dom asked about 1 and 4. Let's take a look at those. Question number 1 is a hanging mass, and they're asking about the tension in the slanted cord. And I'm going to draw a free body diagram here, but I'm going to break one of my own rules, which is my rule is whenever you're asked to draw a free body diagram, you never show it in components. You always show the actual vectors. But I'm going to draw the tension cord here that I've drawn, the tension in the cord that I've drawn in red. I'm going to draw that in component form. So I've got a tension in the y direction, and then I also have a tension in the x direction. Those two tension vectors, those two components represent the red tension vector at a slant. There's also a tension vector to the left and a weight vector going down. You should detect that all of these have to be equal and opposite in magnitude. They all cancel out, basically. Not basically, that's precisely what they do. And so I can say that the sum of the forces in the y direction must be equal to 0. That minus that, I'm going to call that positive and that negative. So it's going to be Fty minus mg is equal to 0. I'm going to add mg to both sides. Fty is going to be Ft times the sine of theta is equal to mg. Mg is given to me as 100. So 100 divided by the sine of 30 degrees is going to be equal to what the actual tension vector is right there. The sine of 30 is 1/2, so 100 over 1/2 gives me the 200. Dominic, make sure that answers your question. I'm going to take a look at question number 4, which is another Atwoods machine problem. And so we'll go through that one fairly quickly. In this case, I'm gonna assume that everyone's comfortable with the idea. Why does it do that? Okay. So everyone should be able to look at that and say it's going to rotate that way. There's more weight on this side. There's 0.9 kilograms or 9 newtons pulling. The Earth is pulling with 9 newtons that way, and trying to pull it in the other way with only 6 newtons. So the net force in the system is 3 newtons that will cause the system to move in the counterclockwise direction. F net is equal to ma. I'm trying to find the magnitude of acceleration. That's what the question is asking. It specifically says the 0.3 kilogram object, but they're all accelerating the same. The string's not stretching, so they all have to have the same acceleration. The total mass in the system is 1.5 kilograms times A, and the net force in the system is 3. And so 3 divided by 1.5 gives me answer D. Dominic, make sure you're good with that. Riley's asking a question about the recording for the live one. I started it with like a little tablet, but to be honest with you, it's like hard to stay in the frame. Like anytime I move, I'm out of the video. I don't know if the stuff that I'm writing on the whiteboard comes out really well, so I kind of bailed on it. So Riley, the short answer to your question is no. Although I honestly think that there should be a way for us to do this pretty effortlessly. It's in progress. I really think that should be something that by the midpoint in the year we've solved that problem. I should be able to capture aspects of class and just record that. I'll get back to you on that, but it's definitely got me thinking. Jess, when you said number 2, do you mean multiple choice or free response question? And I think I'm caught up. If I missed one of the questions that you asked in the chat, please ask it, because I feel like I'm winding down. I'm looking at FRQ, sorry, multiple choice question number 2 on packet number 2. And so here's a kind of a sketch of these 2 blocks. And we have another third law question. The 3 kilogram block is pushing on the 2 kilogram block with the same force. This is an action reaction force pair. So I'm going to write this as F of 3 on 2 is the same as the F of 2 on 3. That's what they ask. They say the force that the 2 kilogram block exerts on the 3 kilogram block. Don't let that like freak you out in any way. So I'm just going to draw the 2 kilogram block, the free body diagram of that. It's on a flat surface, and we know that there's a normal force. We know that there's a weight. The system is frictionless, so the only force pushing it to the right is F of 3 on 2. It's effectively a normal force being pushed on it by the larger block here on the left-hand side. Wherever that is coming from, nonetheless, F of 3 on 2, which is what I'm looking for, is the same as F of 2 on 3. The way I'm going to solve this is by saying, well, F of 3 on 2, whatever that force is the net force, because that's the only force that's accelerating the 2 kilogram block. So that's equal to mass times acceleration. So F of 3 on 2 is equal to the mass of that smaller block, 2 kilograms, times the acceleration of that block. Well, I got to answer the acceleration question for the entire system. So F net is equal to mass times acceleration. The net force is 20 newtons. The total mass is 5 kilograms. It should be clear that the acceleration is 4 meters per second per second. I can now put that in there. F of 3 on 2 is equal to 8 newtons, which is equal to the reciprocal force of F of 2 on 3. Make sure that I have answered your question, Jess. Ryan asks, is there anything in the review session that you'd recommend us reviewing? I would say that there's enough, there should have been enough questions there's a couple of classes of questions that you can prepare for. Here's the string tension question. Here's, the force, the kind of reciprocal force, the Newton's third law force, which is almost identical to the train car problem. What's the, if this is car A, B, and C, what's the tension in the string between B and C? There's just certain types of questions that show up enough that you should be aware and comfortable with how they work. That in an Atwoods machine problem. So as I scan through here, I'd break this unit down into Atwoods machines, string tension, spring forces like this one in question number 5. Make sure you're comfortable with Hooke's law. objects on inclined planes. You guys haven't asked too many questions on that, which is good, but it'll show up. I mean, here they are again. Here's question number 10 on review packet number 2. You're asked to solve for the tension in one of those chords. There's the stop sign looking thing hanging, objects in inclined planes. I feel like they really boil down to a couple of different buckets, if it makes sense, Ryan. So nothing specifically. Hooke's law on the yellow sheet, it should be. I should know that off the top of my head, but I don't. I rarely reference the yellow sheet. But I'm pretty sure that it's there. So I'll leave it at that. If it's not, it's an easy one to memorize. There were a couple of questions. Allie's asking question number 4 on packet 3. Letter E on the first FRQ in packet 2. Adam's saying is if there's time to explain how to approach FRQ 2, part C, which FRQ, Adam, are you referring to? Which review packet? 1, 2, or 3? So let's see what we can do here. 4, let's take a look at 4 on review packet number 3. That's, we did this elevator problem already, so hopefully we caught that on the recording, and then you'll be able to catch that there. Allie, that's for you. Question 4 on review packet 3, I think we did earlier in the session. Adam's saying packet number 3, FRQ 2C on packet 3. All right, let's take a look at that. Free response question number 2 is a bit of a tricky question. I can see how that was tough. So let me kind of re-familiarize myself with the question. So an airplane is accelerating and a physicist passenger holds up a thin string of negligible mass to which she has tied her ring, which has mass m. She notices that the plane accelerates on the runway. The string makes an angle theta as shown. So part B says we determine the length of the runway, 975 meters, and then determine the angle theta that the string makes with the vertical during the acceleration. So so we know, if we go back to the sketch of the ring just wants to sit where it is. And so, everybody in the plane is accelerating to the right. And so the ring itself, I know this seems like weird, but the ring itself actually also has to accelerate. What is accelerating the ring? Well, this tension force can be resolved into its components. There's an x component of tension that is accelerating the ring. Of course, there's also a y component of tension that's equal in magnitude but opposite direction to the weight. So the ring is not accelerated up or down, but it's the x component of the tension that accelerates the ring with everyone else in the plane. So we can kind of see what's going on here in the free body diagram. The sum of the forces is not 0. The x component is equal to the net force. And as we saw in the free body diagram, the y component minus the weight is equal to 0. So we get these two simultaneous dynamics equations. I'm going to resolve the x component into its trigonometric form by just saying ft sine theta. Notice that I've referenced the vertical or the y-axis, so the sine and cosine pieces flip. So we got t sine theta is equal to ma, and then t is equal to ma over sine theta. And then over on the other side, I get t cosine theta is equal to mg. This over here should be also, you should be pretty comfortable with. So I get these two different expressions. T is equal to mg over cosine theta. So then we're stuck. we're done. We don't know what theta is, and we don't know what tension is. And then over here, we don't know what tension is, and we don't know what theta is. So we have simultaneous equations. We have a system of equations. We have two unknowns, but the same two unknowns have two different equations. So we set them equal to each other. We set this ma sine theta equal to mg cosine theta, and then solve for theta. That's exactly what we've done here in this next step. The masses cancel out. I end up getting a over g, and then sine theta over cosine theta is equal to tangent theta. It's a bit of a tricky question. I think the solution's tough to get, but certainly not undoable. Adam, make sure if you have any follow-up questions on that, you let me know what they are. Let's take a look at a follow-up question that I had on packet number 1. Dominic did scan the yellow sheet and said Hooke's law is not on there. So you'll just need to know F equals Kx. Here's review packet number 1. Let's take a look at question number 23. The parabola shown to the right is a graph of speed as a function of time for an object. This is a really cool question because this is the kind of stuff the College Board likes to do. You haven't seen a velocity versus time graph that is quadratic. You've seen graphs that look like this for a velocity versus time graph. And the slope of that line is your constant acceleration, right? If this were an acceleration graph, then the slope is the same everywhere on that blue line. And so the acceleration would have some value. So now they're saying, well, okay, so if you understand that relationship, let's take a look at this. Now we have an acceleration graph that is initially flat or just above 0 and getting more and more positive. What is that telling us? It's telling us that the acceleration is initially small. Then the acceleration gets larger. And then at the end, the acceleration gets really large. And that's because the slope of the tangent line keeps getting larger. We should know that the slope of velocity is acceleration. So the acceleration is changing. And since Newton's second law tells us that if the acceleration is getting bigger and the mass isn't changing, then the force has to follow suit. In other words, the force has to be getting larger. And so we get an acceleration graph that's increasing linearly. So the red one was the slope of the constant velocity graph. This one that I'm going to draw in green is the acceleration graph of a quadratic. And so whatever acceleration does, force is going to do with it. Make sure that I've answered your question on number 23. There was another FRQ, the letter E on the first FRQ. This is a Livy question. First FRQ in packet number 2. Let's take a look. And then we'll probably wrap it up there. Okay, so in this one we have, I want to make sure that I'm doing the right one. Letter E specifically is the question. Yeah, so this is a bit. I think E is definitely tough. It's a stretch for sure. But if we look at the sketch and the corresponding free body diagram, we can see that there is a normal force. However, again, I'm going to break my rule here. The applied force at whatever they're calling F1 has a y component and it has an x component. And so if this force gets really large, then the normal force gets smaller, right? So let's call mg, just for sport, let's call it 10. If the y component of F1 is 8, then the normal force will only be equal to 2. And as this force, F1, gets larger, and maybe goes from 8 to 9, then the normal force gets smaller. It goes from 2 to 1. And eventually, at some point, if F1 gets so big, the Y component is equal to the weight, and there is no more normal force. At that point, the box just starts to lose contact with the ground. And that's really what's happening, or what's being asked about in question FRQ 1 part E. They're asking to derive an expression for the magnitude of the greatest acceleration that the block can have and still maintain contact with the ground. They're really asking you about that point where it just starts to break free. So when I've written F max here, I'm talking about F1. So F max cosine theta is the x component of F1, and we're going to subtract from it. Wait a second, let's take a look at theta. Yeah, so cosine is the x component of F1. So the sum of the forces in the x direction here is not equal to 0. And so we're saying F max cosine theta is equal to MA max. You might be asking, well, what happened to the frictional force? Well, when we lose contact with the ground, when we're at that threshold, the normal force is 0. We know that friction is dependent on the normal force. So when the normal force goes down to 0, friction becomes 0. And so our dynamics equation effectively simplifies. It's just F cosine theta is equal to F net. That's it. There is no frictional force. And in the y direction, there's no normal force. We get F max sine theta, which is the y component of F1, minus mg is equal to 0. And so we have these two expressions for F max. And we just rearranged for F max in equation number 1 in this third line right here. We just divide both sides. Sorry. I've gotten a little ahead of myself. In this third line, let me get a change of pen color. In this third line right here, we're finishing what we did here. We're just dividing both sides by sine theta. We've added mg to both sides and then divided by sine theta. So F max is equal to mg over sine theta, and then we're putting that into the x equation. So we're taking mg over sine theta and plugging it in right here. This is more algebraic kind of like cleverness and savviness more than it is being a physics student at this point. So we get mg sine theta times cosine theta. That's really what happens. We get cosine theta over sine theta. If it were sine theta over cosine theta, that would be tangent theta. Cosine theta over sine theta is cotangent theta. If you had left it that way, I think that's Shani's question. If you had left it that way, then I don't know. I think the scoring guidelines are pretty specific about whether you would have to write it as a final answer, cotangent or tangent, in order to get full credit. You know, I'm not really sure. I'd have to look at the scoring guidelines for this question. I think you should when you can. All right, just before I wrap things up, a couple of things. Allie asked about multiple choice. It's roughly 20 to 24 multiple choice questions. I can't remember off the top of my head, and 3 FRQs. You'll need the entire block, so you don't want to show up late. As a matter of fact, I'd get there at least a couple of minutes early if you can. Unpack, get a seat, take out your yellow equation sheet, calculator, check degree mode, and be ready to go. There is a bubble sheet for the multiple choice questions. All right, I'm going to wrap up there, and if you guys have questions, you can see me in the morning. If you have recommendations on how to make these review sessions better, please let me know. I've got a few ideas, but send me an email and give me ideas and say, hey, maybe you could do this during a review session. I'd appreciate it. All right. I'm going to stop there. See me in the morning if you have additional questions. Have a good night.